Welcome to ODEs lesson 26, the solution of x prime equals b times x, where the matrix B is not diagonalizable. We are going to consider the system of first-order linear differential equations of the form x prime equals matrix B times x of t. We'll assume that this matrix B is an n by n matrix and does not have a set of n linearly independent eigenvectors. However, B does have a set of n linearly independent generalized eigenvectors. Using those n linearly independent generalized eigenvectors, we can find a set of n linearly independent solutions to the system of equations, ordinary differential equations, x prime equals the matrix B times x of t. From this set of linearly independent solutions, we can write down the general solution to the system of ordinary differential equations, x prime equals b times x. Let's look at the following example. Let's solve basically x prime equals b times x. X in this case is a column vector with 3 components. Here's our matrix B. So what do we have to do to solve this system of differential equations? The first thing we need to do is to find the eigenvalues by considering the characteristic equation. The determinant of b minus lambda times the identity equals 0. So here is the determinant, and this is the matrix b minus lambda times the identity. It's similar to the matrix B, except we're subtracting lambda times the identity, which means we're subtracting lambda from each of the main diagonal terms. And so we want to set this determinant equal to 0. When we factor it, when we evaluate this determinant and factor it, we'll find out that we have minus the factor lambda plus 4 times the factor lambda minus 5 squared equals 0. So from this, we can see that the eigenvalues are minus 4 with multiplicity 1 and 5 with multiplicity 2. We can get this using SageMath the following way. First, I'll declare some variables, x, y, z, t, u, v, and alpha. I'm going to use alpha here instead of lambda, because lambda has a special meaning in SageMath and I guess also Python. So we declare these variables, there they are. Now we'll define the matrix B that we have up here. So it's a matrix, and then here are the first row, second row, third row. Notice in each row the elements are separated by commas. The row is enclosed in square brackets on the left and on the right, and the whole matrix is also enclosed by a square bracket on the left and one on the right. So we define B to be this matrix, and then we'll show B. This will display the matrix B, which we see is the same one that we have right here. Next, we need to define the identity matrix, and the way to do that is to say I equals matrix dot identity, and then to get a 3 by 3 identity matrix, we'll put the parameter 3 in here. And then after we create this matrix, once again we want to display it down here, so we have the second command, show I. And so here we can see that we have the matrix that we wanted, 1s on the main diagonal, 0s above and below the main diagonal. To compute the determinant of b minus alpha I, we can use the built-in determinant function, det, determinant of b minus alpha I. If we want to actually show the results of that computation, we have to use show. So show, and inside parentheses, the determinant of parentheses b minus alpha I. When we execute this command by hitting Shift Enter, we get that the determinant is this polynomial. It looks kind of messy, and in fact we can see that what we have here are parentheses here, another parentheses for a plus 40 times a plus 39. This last parentheses matches with the first one here, plus 1564 times the quantity alpha minus 7, plus 12 alpha minus 128. I want to solve for alpha. This is not a nice equation to set equal to 0 and to solve for, well, actually getting ahead of myself, not the characteristic equation yet. But here's the determinant in a fairly messy form. So let's do the following. Show the determinant of b minus alpha I dot factor. And notice that this last parentheses here matches with the parentheses after show. And when we execute this statement, we get minus alpha plus 4 times alpha minus 5 quantity squared. So from this, we can see that if we set this characteristic polynomial equal to 0 to get the characteristic equation, the solutions are going to be alpha equals minus 4, and it has multiplicity 1, and alpha equals 5 with multiplicity 2. Well, in our problem over here, we decided to use lambda, and over here we decided to use alphas instead because of, I guess you can say, a quirk of SageMath. So what we see are we have lambda 1 is minus 4 with algebraic multiplicity 1, and lambda sub 2 equals 5 with algebraic multiplicity 2. So let's recall that this is the differential equation that we have. X prime equals b times x. We're looking for the eigenvector or eigenvectors corresponding to lambda equals minus 4. So b minus a minus 4i, which is equal to b plus 4i, is this matrix, just adding 4 to each of the principal diagonal terms. When we do this simple calculation, b plus 4i is this matrix. So we want to solve b plus 4i times an eigenvector equals the 0 vector. And so we take the reduced row echelon form of this augmented matrix. This part is b plus 4i, and we have zeros for this last column in the augmented form. When we look at the reduced row echelon form of this augmented matrix, we get this. So we look at this, and v1 is going to be a leading variable, v2 is going to be a leading variable, and v sub 3 is going to be a free variable. So let's let that free variable v sub 3 equal t, and then solving v1 plus 8 over 371 v3 equals 0, we get that v1 is this. Similarly, solving this equation for v2 in terms of v3 gives us v sub 2 is 153 over 371 times t. Okay, so t can be anything, and as long as it's not 0, and we will get a non-zero eigenvector corresponding to lambda equals minus 4. To make it as simple as possible for later, let's let t be 371 so that we don't have these fractions to worry about. And in that case, v1, v2, v3, that vector is -8, 153, and 371. We only had one free variable, v3, so we only get one eigenvector corresponding to lambda equals -4, up to a constant multiple t, basically. And that's fine because the algebraic multiplicity equals the geometric multiplicity, which is 1 in this case. And so we can move on to the next eigenvector or eigenvectors. Oh, one more thing to notice here before we go. Here's a little bit of SageMath code. We look at b plus 4i and calculate the reduced row echelon form of it, which is what we're doing right here. And we get this matrix, which is what you saw over here. Okay, we want to find the eigenvectors of B corresponding to the eigenvalue 5. So we're going to look at B minus 5i times an eigenvector equals the 0 vector. The augmented matrix for this vector equation, the system of equations, the augmented matrix for the corresponding system of equations is this. Remember, we have 0 on the right-hand side as a column. That gives us a column of zeros here. So the augmented matrix, after doing the arithmetic for b minus 5i, is this matrix right here. Now, to solve these equations, we need to get the reduced row echelon form of this matrix. And it turns out to be this matrix here. Looking at the first row, we see that v1 is a leading variable. From the equation corresponding to the second row, v2 is a leading variable. We don't get any more leading variables from the third row. That leaves v sub 3 to be a free variable. So let's set v sub 3 equal to t. Then looking at this first equation, 1 times v1 minus a half times t equals 0 gives us that v1 has to be a half t. Looking at the second equation corresponding to the second row, 1 times v2 equals 0, which forces v2 to equal 0. So what we then get is that v1 is a half t, v2 is 0, and v3 is t. If we decide to let t equal 2, then we get that v sub 3 is 2, v sub 1, which is a half t, is 1, and v sub 2, which is 0, has to be 0. So v1, v2, v3 have to be 1, 0, and 2. In this case, we only got one eigenvector up to a factor, a constant factor. We could have used another value of t. For instance, if t were 4, then we would have had 204 here, which would have just been double what this one was. So basically, we just get one eigenvector up to a constant multiple. And here we have a problem, because 5 had algebraic multiplicity 2. But what we found here is that we only had one eigenvector. The geometric multiplicity of this eigenvalue, the geometric multiplicity is 1, although the algebraic multiplicity is 2. So we have a problem here. This 3 by 3 matrix only has 2 linearly independent eigenvectors. If we were to diagonalize it, we would need 3 linearly independent eigenvectors for this 3 by 3 matrix, and this matrix just doesn't have them. So this matrix B is not diagonalizable. We're going to have to see how to handle this case. So, what do? Let's suppose that the characteristic equation of B in factored form is the following. The determinant of B minus lambda I, which many people just write B minus lambda. Let's suppose that it's lambda minus an eigenvalue lambda 1 raised to the m1 power times a factor lambda minus lambda 2 raised to the m2 power all the way through lambda minus lambda sub k to the m sub k power equals 0. How do we handle it? Because we have algebraic multiplicities of m sub 1, m sub 2 through m sub k, but the geometric multiplicities might be less. So here's what we'll do. For each I, we will find a set of m sub I linearly independent solutions to this equation, b minus lambda sub I times the identity raised to the m sub I power times a vector that we solve for equals the 0 vector. This vector v here is called a generalized eigenvector of B associated with lambda sub I. So let's find the generalized eigenvectors for our lambda sub 2 equals 5. So B minus 5i is this matrix. If we square that matrix, B minus 5i quantity squared is this matrix. So let's solve this for the generalized eigenvectors. B minus 5i squared times this vector, this generalized eigenvector, equals 0. We have the square here because lambda sub 2 equals 5 was an eigenvalue of algebraic multiplicity 2. So, to solve this, we will look at b minus 5i squared, which is this matrix here, augment it by a column of zeros, thinking of this as a system of linear equations. And we want to solve basically 16v1 plus 16v2 minus 8v3 equals 0, and so on, 3 equations. To solve those, let's get the reduced row echelon form of this augmented matrix. Turns out to be this. If we look at this, v1 is a leading variable, and that's the only leading variable. So the other two variables, v sub 2 and v sub 3, have to be free variables. So this first equation is basically just 1v1 plus 1v2 minus a half v3 equals 0. Here are the coefficients, basically. And so we know v2 and v3 are free. So we can let v2 be s, we can let v3 be t, and pick different values for s and t. But I'll just leave it in this form. And first, let's let v sub 2 equal minus 1 and v sub 3 equals 0. If we plug those into this equation, we get that v1, v2, v3 is 1 minus 1, 0. Similarly, if we let v sub 2 equal 0 and v sub 3 equal 1, substitute into this equation, we get that v1, v2, and v3 are a half, 0, and 1. These two vectors are linearly independent. That's easy to see since they're not multiples of each other. And we only get two generalized eigenvectors for lambda equals 5 because the multiplicity, algebraic multiplicity of the eigenvalue 5 was 2. So these are two linearly independent generalized eigenvectors corresponding to this eigenvalue. So let's suppose that we have n linearly independent generalized eigenvectors for this n by n matrix B. How do we go from those generalized eigenvectors to solutions of the system of ordinary differential equations? Well, suppose that characteristic equation for the matrix B has a factor of lambda minus lambda sub I raised to the m sub I power in its full collected factorization, let's say. And if V is a generalized eigenvector for that eigenvalue lambda sub I, then here is what one solution of that system of equations looks like. It's a vector equation. This f sub I is a vector, a column vector. F sub I of t is e to the lambda sub I t times v, a constant times this generalized eigenvector, plus this constant t e raised to the lambda sub I t times this matrix b minus lambda sub I times the identity times that generalized eigenvector v, plus more terms corresponding to this m sub I here. We have a t squared over 2 factorial exponential, this stuff squared times v, plus all the way through t raised to this exponent over this exponent factorial, e raised to this exponent times this matrix raised to this exponent times v. If you look at this, it looks something like a Taylor polynomial. So for each one of those generalized eigenvectors, we get one of these solutions. Since we have n generalized eigenvectors for that n by n matrix B, that means that we have n of these functions. We get one of these functions, one of these solutions for each distinct generalized eigenvector from that set of linearly independent generalized eigenvectors. So once we have these n solutions, to get the general solution, all we have to do is take a linear combination of them, an arbitrary linear combination. The general solution to x prime equals b times x is this. Arbitrary constant c1 times the solution f1, plus an arbitrary constant c2 times f2, plus all the way through an arbitrary constant c sub n times f sub n. So this will give us the general solution to x prime equals b times x. If we have an initial value problem, we can use the initial conditions to determine what c1, c2 through cn are. So let's see. We found that this vector, minus 8, 153, 371, is an eigenvector of this matrix B corresponding to lambda sub 1 equals minus 4. So that tells us that part of the solution to that system of ODEs is f1 of t is e to the minus 4t times this eigenvector. Now, to check that, we want f sub 1 to satisfy this equation. So that means that f sub 1 prime should equal b times f sub 1. So the derivative with respect to t of f sub 1 of t should equal b times f sub 1 of t. Let's check that using SageMath. To compute this left-hand side, we'll look at the derivative of the exponential of minus 4 times t times this matrix minus 8, 153, 371. And remember, we're differentiating this with respect to t. When we show the result of this calculation, it's this column vector. On the other side, we need to compute b times f sub 1. So here's the computation, b times, and then f sub 1, once again, is that exponential times that column vector. right up here, okay? And then whatever the result of this calculation is, we want to show what the result is, and the result is this column vector. If we look at this column vector and this column vector, we see that they are identical. So the left-hand side of this equation, which computed by SageMath, is this. The right-hand side of this equation, which is computed in SageMath as equaling this, they are the same. They are equal. So now let's move on to the other eigenvalue, lambda sub 2 equals 5. We saw before that this is a generalized eigenvector. Lambda 2 equals 5. 5 was an eigenvalue of multiplicity 2. So part of the solution to the ordinary differential equation, the system of ordinary differential equations, is the following. F sub 2 is going to be e to the lambda I t times that generalized eigenvector plus t times e to the lambda I t times b minus lambda I times the identity matrix times v. Okay? Now let's see. Lambda in this case is 5. So this first term is e to the 5t times this generalized eigenvector. Then the second term is t e to the 5t, which corresponds to this part, b minus lambda I times the identity. In other words, b minus 5 times the identity is this matrix here, and it's multiplied by that generalized eigenvector, which is 1 minus 1, 0. Okay, now this term is right here, unchanged. We have to do a little bit of calculating on this term. This matrix times this column vector turns out to be this column vector, minus 1, 0, and 2. And so, putting it all together, f sub 2 of t, another solution to our system of differential equations up here, is e to the minus 5t times this vector plus te to the minus 5t times this other vector. So now, let's check to see if this is really a solution to the differential equation. Does the derivative with respect to t of f2 equal b times f2? Yes or no? Well, let's look at it up here. We'll define f2 to be, let's see, this term, which is e to the 5t times the matrix, column matrix 1, 1, 1, minus 1, 0, plus this second term, t e to the 5t times the matrix, which is a column vector, minus 1, 0, minus 2, which is what we have here. So here is f2. Show f2 of, and then t equals t here. It looks a little bit confusing, but basically, in order to make vector functions work correctly and matrix functions work correctly, we have to substitute t in for the t that occurs in this formula. Who knows? So anyhow, here it is. And you can see that it really is the same thing that we have here. This first component, e to the 5t times 1, that's right here. T e to the 5t times minus 1, that's this part right here. Similarly, the second one, minus 1 times e to the 5t plus 0 t to the 5t is just minus e to the 5t. The third component here turns out to be the third component here. So now let's differentiate f2 of t with respect to t and show the result. Here it is. That's the computation of the left-hand side. The computation of the right-hand side, I'm going to call it g for a minute, b times f2 of t, and then I'll show what g of t is. Turns out to be this. This is b times f2 of t. If we look at this column vector and this column vector, they are identical. So this column vector does equal this column vector. F2 does satisfy this system of differential equations that we have up here. Let me mention one more thing. In order to get this to work in SageMath, when we differentiate F2 with respect to t, before you differentiate it, you have to substitute in t for the t. Similarly down here. So if you just have F2 of t here, a quirk of SageMath, it just doesn't work right. We had a second generalized eigenvector corresponding to the eigenvalue 5. It was this one, 1/2, 0, 1. So that will give us another solution, which I'll call f sub 3 of t, to this system of equations up here. F sub 3 of t is going to be e to the lambda sub I t times this eigenvector, generalized eigenvector, plus t e to the lambda sub I t times b minus lambda sub I times the identity times that generalized eigenvector. So let's see what happens here. This first term is going to be e to the 5t times this generalized eigenvector. And then the second term is going to be t e to the 5t. Here is b minus 5i times this vector, 1/2, 0, 1. Okay, now it turns out that when you multiply b minus 5i times this generalized eigenvector, it turns out to be 0, 0, 0. And so f sub 3 of t turns out to be e to the 5t times this vector, which we have right here, plus t e to the 5t times this stuff, which turned out to be 0, 0, 0. And so all we get is this first term. This first term plus 0 is just this first term. So f sub 3 of t equals e to the 5t times 1/2, 0, and 1. Now, you might ask yourself, well, why did I get zeros here? Well, 1/2, 0, 1 we saw earlier, besides being a generalized eigenvector of b, was also an eigenvector of b, corresponding to lambda equals 5. So b minus 5i times that eigenvector was the 0 vector. So in any case, we just get that f sub 3 of t is this exponential times this vector. Now we can use SageMath the same way as we did previously to check to see if f sub 3 satisfies the system of differential equations. So we, in this first cell, define f sub 3 to be this function. We can see it right here. In the second cell, we differentiate f sub 3 with respect to t, and we get this column vector. In this third cell, we multiply b times f3 of t, and we get this result. Comparing these two, we can see that the derivative of f sub 3 is equal to b times f sub 3. This is true. The derivative of f sub 3 of t is equal to b times f sub 3 of t. That means that f sub 3 of t satisfies this equation up here, x prime equals b times x. So this is a third solution to our differential equation. We have found 3 linearly independent solutions to our 3x3 system of first order differential equations. So now we are ready to write down the general solution to x prime equals bx, which in our particular problem is this matrix times x. we had one eigenvector corresponding to eigenvalue -4. And this gave us the solution f sub 1 of t is e to the -4t times this vector. We also had a generalized eigenvector corresponding to eigenvalue 5. And this gave us the solution e to the 5t times this vector plus t e to the 5t times this vector. We had another generalized eigenvector for eigenvalue 5, which also turned out to just be a plain old eigenvector also. And here it is right here. And that gave us the solution f sub 3 of t is e to the 5t times this vector. So the general solution, x of t, is c1 times f1 of t plus c2 times f sub 2 of t plus c3 times f sub 3 of t. If we had initial conditions for an initial value problem, we could use those initial conditions to find C1, C2, and C3. Notice that f sub 2 of t consisted of two terms here. So C2 times f sub 2 of t was C2 times those two terms that comprise f2 of t. These are all the solutions to x prime equals this matrix times x. So what did we do in this lesson? We considered the matrix equation x prime of t equals bx of t, where B is an n by n matrix, and in this case B does not have a set of n linearly independent eigenvectors. When that happens, B does not have linearly independent eigenvectors, but it does have n linearly independent generalized eigenvectors. So for each of these generalized eigenvectors, which we can compute, we found a solution to the system of ordinary differential equations. That gave us n linearly independent solutions. Then we took an arbitrary linear combination of these n linearly independent solutions to write down the general solution to x prime of t equals bx of t, b times x of t. I hope that you enjoyed this lesson. Thank you for watching, and please stay tuned for further videos. Have a nice day.